Today's lesson is going to be discussing roots and radical expressions. We've looked at radicals before. A radical, simply remember, was our square root symbol. And we took the square root of a number, say 16, and it gave us 4. In this case, we saw that we took the square root, or the second root, of 16. So that asks us what times itself, or what twice, gives us 16. In that case, it's 4. If we look a little deeper into this little 2 is what we're going to be changing today. We call this the index. The number under the radical symbol is called the radicand. And then also we have the radical symbol. So we're going to be changing that index today. So we're going to take it to the third or to the fourth or to the fifth root. So let's go ahead and look to start with of our real roots. And simply what real roots means is what numbers under the real number system will give us whatever index or whatever root we have of a number. So let's take that square root of 16 again. Now if I ask you to find all of the real roots, well, we know that 16, 4 times 4 gives us 16. And we also know that negative 4 times negative 4 gives us 16. If we continue with this, if we take the fourth root of 16, now I'm asking myself what times itself times itself times itself gives us x to the fourth. Notice I put in x's because I'm not for sure what that is. Well, in this case, if I think about 2, 2 times 2 times 2 times 2 gives me 16. So I get 2 and I get negative 2. Since negative 2 also gives me 16 when I multiply it to itself 4 times. Now if we were to look at, say, the cubed root, and this time let's take the cube root of 8. Here I'm asking myself what times itself will give you 8. So 2 times 2 times 2 gives me 8. So I get 2. If we go back to what we were talking about with these two roots, remember we had a positive and we had a negative. Well, does a negative work for us here? Can I take negative 2 times negative 2 times negative 2 and give me a positive 8? In this case, no, it doesn't. Negative 2 times negative 2 is positive 4 times negative 2 gives me negative 8. So negative 2 doesn't work. We only get the positive. But if I ask you for the third root of negative 8, here we would get a negative 2. So notice if my index, in this case, remember my index was 2 since there's not one there. If my index is even, I can get 2 possible solutions. But if it was odd, I'd only have 1. And it's going to be whatever that number, the sign of that number under the radical is. So in this case it was positive, I end up with positive. Here it was negative, so I end up with negative. It may be useful to have your perfect thirds and perfect fourths listed out off to the side on a piece of paper. I'll get you started, you can finish. 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, and 5 to the third is 125. You may want to list out to about 10. Same thing with your fourths. 1 to the fourth is 1, 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth, now I gotta think, 256, and 5 to the fourth is 625. Normally don't go much higher than 5 to the fourth, so that would probably be a big enough list. Take your third roots out so you get a little more idea of what numbers we can work with. So that goes through the real roots of a number. Now let's go ahead and look what happens if we have variables under those radicals. So what happens if I gave you the square root of 4 x to the 4th y to the 6th. And if you remember, we talked about this earlier in the year when we took the square root of 4. That gave us 2. And what we did was we took those exponents and we divided them by 2, or what the index is. So in this case, we get x squared and we get y to the 3rd. But let's talk about this for a little bit. If I were to look at y to the 6th, y to the 6th, it doesn't matter what that value of y is, it will always be a positive number. Anything to an even exponent ends up being a positive number. But if I come over here to my solution and I look at y to the 3rd, well, y to the 3rd, if y were negative, then that would end up being a negative number. Because remember, anything to an odd exponent gives us whatever that sign is. So, for example, if my y value was 2, so y to the 1st would be 2, y squared would be 4, y to the 3rd would be 8, y to the 4th, 16, y to the 5th, 32, and y to the 6th would be 64. But if my y value were negative 2, now I could get negative 2, 4, y to the 3rd would give us negative 8, 16, negative 32, and then y to the 6th would give us positive 64. Notice how my negatives alternated between positive and negative. What we want to do is to make sure that we only get a positive value out from under here. Remember, if it's not positive, then we end up with imaginary numbers. So in order to make sure that that y to the 6th stays positive, we're going to put it in absolute value. X squared, if we look at x squared, we don't need the absolute value because x squared is always going to be a positive number. Same thing with x to the 4th. It was positive, so this is going to stay positive. So we're going to end up with a positive solution out of this. Doesn't matter what our x or our y value was, it'll always be the positive value. Let's go ahead and look at another example. Here, let's take the 3rd root of 27 x to the 6th, y to the 3rd. Now remember, taking the 3rd root of something is going to give us whatever the sign is of that number. So the 3rd root of 27 gives us 3, because 3 times 3 times 3 is 27. The 3rd root of x to the 6th, here I'm going to take my 6th power divided by the index, and I get x squared. And for my y's, 3 divided by 3 gives us y to the 1st. Now you may be asking yourself, do we need absolute values on our y to the 1st? And in this case, no, because remember, if y is negative under our radical, we can take the 3rd root of a negative number and end up being a negative value. So what you need to remember is that if the index is even and we end with an odd exponent, it gets absolute values. If we start with an odd index, we don't need absolute values at all. So let's go ahead and look at another example. I know it's a little tricky. So let's take the 4th root of, say, 256 x to the 8th, y to the 12th. So here, the 4th root of 256, remember from our list, I have 256. The 4th root of 256 would be 4 to the 4th. So I end up with 4. Taking 8 divided by 4 gives me 2. And 12 divided by 4 gives me 3. Notice our x squared, we have an even exponent. Our y to the 3rd is odd, and we started with an even index. So we need to go ahead and put those absolute value symbols around our y to the 3rd. Let's go ahead and look at one more example, just for some good measure, and we can talk a little bit about what you're going to see within your assignment. And here I'm going to take, say, the fifth root of the quantity x plus 1 to the 15th. Here, I have an entire quantity to an exponent. I can't multiply that 15 in because of that plus sign. But what I can do is take that exponent and divide it by the index and end up with x plus 1 to the third power. 15 divided by 5 gives me 3. Do I need the absolute value symbols? Well, I end it with an odd, so that would say probably, but I start it with an odd index. Since I started with that odd index, I don't need the absolute value because that inside could be positive or negative, and my solution will be either positive or negative based off of what my radicand is. And that'll conclude our radicals and simplifying radicals. The things you need to remember is that the index is the number we're taking the root of, the radicand is under the radical, and we have our radical symbol. If we take an even index, we can have the positive or negative values. But if we have an odd index, then our sign is going to be simply what our radicand sign was. So it was positive stays positive, negative stays negative. To simplify radicals that have variables in them, if we start with an even index and we end with an odd exponent, we need to put absolute values around those odd exponents and that base. Even exponents don't need the absolute value symbol. If we start out with an odd index, we don't need absolute values at all. Again, even indices, odd exponents need absolute values. Odd indices don't need absolute values at all. And that concludes our roots and radical expressions.